Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So, that's about the magnetic field produce, how we can produce and represent magnetic field. Here we have three things when we discuss about the electric current, magnetic magnet that comes from electric current, or we call it as the electromagnet. We have long straight wire, and then current carrying rope, and also solenoid. Each of them we will discuss. The first one we will discuss about the direction. Remember the direction, we have right hand rule. Our thumb will be in the direction of electric current or electric current, and the other fingers will be the B, the direction of magnetic field. So, if we use something like this, our thumb will be electric current, the forefinger will be in the magnetic field. We can use to manage the direction. For example, remember in force, if we have force 1 coming to the right, 1 coming to the left, so the total force will be right minus left. And if we have two forces coming to the right, both of them coming to the right, so the total force will be the sum of those two forces. Here the same, because the magnetic field having the direction, so we have to make sure in which direction the magnetic field will be. If they have the same direction, so the total will be the sum all of them. But if the direction is different, opposite, the total will be, we need to subtract the magnetic field. So, the first one, we will talk about the long straight wire. Long straight wire. So, on the first one, we will discuss about the direction. The direction, we will use the right hand rule, means that from here, easily we can use our finger and our thumb. The thumb will be in the electric current, the forefinger will be the direction of the magnetic field. And then the second one, we will discuss about the magnitude. The magnitude for this long straight wire will be B equals mu 0I per 2PR. So B is the magnetic field, we discussed about that one, the unit is in Tesla or T. I is the electric current, the unit is in ampere. And then R is the radius, the unit is meter. And mu 0, it is constant magnetic permeability of free space, which is 4p times 10 to the power of minus 7 Newton per ampere square. Take a note for this one, so we will continue for the example. The example for the long straight wire. What is the magnetic field strength at distance of 0.05 meter from long straight wire carrying current of 5 ampere? What we have in the questions, we have the distance and also the current. So let me write it. The distance is R, 0.05 meter, and the current I is 5 ampere. And also we have mu 0, which is 4 pi times 10 to the power of minus 7 Newton per ampere square. And we want to find the magnetic field. As mentioned before, for long straight wire, we have the equation for magnetic field is mu 0 I per 2 PR. Put all the numbers in the equations. 4p times 10 to the power of minus 7 times 5 per 2p times 0.05. So 2p and 4p we can cancel it, go to 0.05 and 5, we will get 100. So rearrange again, 200 times 10 to the power of minus 7, or we will get 2 times 10 to the power of minus 5. And don't forget the unit of B is in Tesla. It is the first one, long straight wire. Magnetic field of long straight wire. Remember the magnitude mu 0 I per 2pr and the direction. Using the right hand rule, the term will be the electric current for finger will be in the direction of the magnetic field. Next is magnetic field of current carrying loop. Current carrying loop. Same with the long straight wire, we will discuss about the direction and also the magnitude. The direction, we will use the right hand rule. For this, if long straight wire, easily we can use our thumb as electric current, and forefinger will be magnetic field. For this one, will be difficult if we use our thumb as electric current. So to make it easily, we can reinforce our thumb, the right hand rule for the loop and also in solenoid. Our thumb will be the magnetic field, and four fingers will be in the electric current. So we reinforce. This thumb will be the direction of magnetic field that we produce using the current carrying loop, and forefinger because it is in loop, so easily to bend our forefinger to follow the direction of the electric current. Just reverse it, make it easily. And then the magnitude is B equals mu 0 I per 2R. Almost the same with the long straight wire, but in here we don't have P, so 2R. How about the other will be the same, B in Tesla, mu 0 4P times 10 to the power of minus 7. I will be electric current, R is the distance or the radius. How about if we have n number of turns? What happened to the B? So B will be, if we already have this one, we can just multiply it with n. Mu 0 I per 2R. So if we have, for example, 5 turns, so the result of B times 5, 10 turns just times 10, or maybe it is half, so we just times half, or the other. You can we will check in the sample of questions. Take a note for this one, make sure you got everything. Then the example, the first example, we have the magnetic field at the center of circular loop of wire carrying current of 2 ampere is 6 times 10 to the power of minus 5 Tesla. The loop has 5 turns. What is the radius of the loop? We will use P as 3. What we have in the questions, we have the magnetic field is 6 times 10 to the power of minus 5 Tesla. The other we have current 2 ampere and 5 turns. So let me rewrite it. B is 6 times 10 to the power of minus 5 Tesla. Then current I 2 ampere and N is 5. Don't forget mu 0 4P times 10 to the power of minus 7 Newton per ampere square, and we have P 3. So using the equations, B equals, because it is loop, we will use mu 0 I per 2R, and we have N here just times N. So B we have 6 times 10 to the power of minus 5 means 0 for P times 10 to the power of minus 7 times I is 2 ampere per 2R. We want to find the radius times 5. So 2 and 2 we can cancel it. Then what else? I think this one. Okay. Then rewrite it. We have R equal 4 times 3, because we will change P to be 3 times 10 to the power of minus 7 times 5 per 6 times 10 to the power of minus 5. So 3 and 6 we got 2, 2 and 4 we got 2. So we have 10 to the power of minus 5 and 10 to the power of minus 7 minus 2. So we will have 10 times 10 to the power of minus 2, or we have 10 to the power of minus 1. It is in meter. If you want to convert it to centimeter, it will be 0.1 meter and will be 10 centimeter. So the problem is we want to find the radius here and the radius for the loop. The next question is, we have semicircular wire, the radius is 2 centimeter, the current is 4 ampere. You can take a look in the figure, and here it is. So we have the radius. Here we have 2 centimeter and we have electric current is 4. How about the N? Because we have only semicircular, so N will be half. If we have 1 loop, the N will be 1. We have 5 loops, the N will be 5. If the loop is only semicircular, so we will have N is half. Using the equation for loop, B equals mu 0 I per 2R, we can get the put the number into the equations. Don't forget mu 0 for P times 10 to the power of minus 7, I is 4 per, the radius is 2 centimeter, or it is 0.02 meter. 2 times 0.02, so 2 and 4 2, 2 and this got 100. So we will have 40 times 10 to the power of minus 7 and 100, it is minus 5. And if we change 4 to P to 3, we will get this one, 10 to the power of minus 5. Let me check it again. We need to multiply with N. And this one, so we will have 6 times 10 to the power of minus 5. This. So it is about the loop. Don't forget about the direction and also the magnitude. The direction we will use the right hand rule, and the magnitude we will use mu 0 I per 2R. If we have many turns, so just time the turns. Next is solenoid. For solenoid, also we will discuss it in what is the direction and what is the magnitude. For the direction, because solenoid also circular, we will use the same right hand rule as in the loop. Thumb will be magnetic field, the forefinger will be in the electric current. And for the magnitude, we have this one. mu 0 and I per L. So the other will be the same. N is the number of turns we already discussed in the loop, and L is the length of solenoid. As you can see here, the length of the solenoid is this one. Mu 0 and I per L. Mu 0 the same, 4p times 10 to the power of minus 7. N is the number of turns, I is the electric current, and L is the length of solenoid. Take a note for this one, and we will discuss the example of the solenoid, the magnetic field of solenoid. The example is this one. Solenoid of length 20 cm consists of 1000 turns of wire. If the solenoid carries a current of 0.1 ampere, find the magnetic field inside the solenoid. P will be 3. What we have here is we have the length, we have the turns, we have the current. So let me rewrite it. The length is 20 cm. Because it is in centimeter, we have to convert it to meter, 0.2 meter. And then the turns is N, 1000, or we can write it as, but it's up to you, 10 to the power of 3. Then the current, I is 0.1 ampere. If you want, you can write it 2 times 10 to the power of minus 1 meter. This one, 10 to the power of minus 1 ampere. P will be 3, mu 0, 4p times 10 to the power of minus 7 Newton per ampere square. How about the B? Remember, we want to find the solenoid. So we will use mu and I per L. Put all the numbers that we have for P times 10 to the power of minus 7 times N is 1000 or 10 to the power of 3 times the I is 10 to the power of minus 1 per L is 2 times 10 to the power of minus 1. So minus 1 cancel, 2 and 4 cancel. So we'll have 2p times 10 to the power of minus 7 and 3 will be minus 4. Or we can change the p to 3. We have 6 times 10 to the power of minus 4 this. That's the solenoid. Sometimes we will find the, for example, current carrying wire with the loop, or current carrying wire with the solenoid, or solenoid with the loop. It is the combination. Okay, now how about if we have something like this? It is not only circular loop or long straight wire or solenoid, but it is combination. So we have conductor consists of circular loop, radius of 0.2 meter, and it is coming from 2 straight long section, and the wire carries a current of 8 ampere. We need to determine the direction and the magnitude of the magnetic field at the center of the loop. What we have here, we have circular loop, and also we have long straight wire. The radius is 0.2 and the current is 8 ampere. First, we need to determine the direction of each, and then we can calculate the magnitude. For the direction, electric current, long straight wire coming to the left, and at the center it is up, so will be coming in. Let's say in this one is B1 for long straight wire and B2 for circular. So coming to the left, long straight wire, then there will be magnetic field coming in at the center of the loop. So B1 will be cross here, coming in. How about the loop? Loop is in clockwise direction. Remember, when we talk about the loop or solenoid, better we use 4 finger as the electric current, and or thumb will be magnetic field, the direction of the magnetic field. Forefinger, clockwise direction, and then at the center will be coming in as well. So we have cross for B2 because both of them having the same direction of magnetic field. So in total we will have B total will be B1 plus B2. B1 is long straight wire, we have mu 0 I per 2 PR, and B2 is loop mu 0 I per 2R. Put all the number, so we have mu 0, let's write it for P times 10 to the power of minus 7 times I is 8 per 2 P times R is 0.2 plus 4P times 10 to the power of minus 7 times 8 per 2 times 0.2. 2P and 4P we get 2, 2 and 0.2 we get 10. Same here, 2 and 4 we get 2, and 2 and this one we got 10. So we have 8 per 10 is 0.8 times 10 to the power of minus 7 plus this one we have 0.8p times 10 to the power of minus 7. If we change the p, let's say p equals 3, you can get the exact number for this one times 10 to the power of minus 7 plus 2.4 times 10 to the power of minus 7. So we will get 3.2 times 10 to the power of minus 7 Tesla. It is the total. Check again if there is correction, you can tell me. It is the combination between the long straight wire and loop. So on the first, we need to define the direction of its wires. Is it the same direction or different direction? Then from that one, if the direction is the same, we can do sum B1 plus B2, and if it is in the opposite direction, we can do the subtraction. The next example, for example here, it is the same. Let's say this one is the wire 1, this one is the wire 2. For wire 1, thumb is coming up and X is to the right, so there will be cross coming in. Let's say B1 in X is cross, and B2 the electric current is coming downward, and then X is to the left, so it will be coming in as well. So B2 will be cross as well. So B total will be B1 plus B2, and then you can put, because it is the same, mu 0 I per 2 PR and plus mu 0 I per 2 PR and mu 0 I per 2 PD or R here, let's change to D because the distance is D. So we will get 2 mu 0 I per 2 PD, or if this one is D, we can get to D. Something like that. And the last is we have two parallel straight wire 1 meter apart, carry currents of 2 ampere and 4 ampere. At what points between two wire is the magnetic field 0 when both currents flow in the same direction? What we have here is this one. Same direction, let's draw it for example, coming up. And this one is 2 ampere, let's say I1 is 2 ampere, I2 is 4 ampere. Then it is 1 meter apart, and we want to find the magnetic field that having the magnitude of 0. It can be between, or it can be to the left or to the right. If it is one coming in, the other coming out, maybe it will be in between, because if we want to find the magnetic field equals 0, we have to make sure that both magnetic field having the different or opposite direction. One can be coming in, the other coming out. For example, here, let's take a look here. If we have B here, let's say B1, here is B2, this one is B3. If B1 for I1, it is coming up, to the left will be coming out, and from the I2 coming up, and to the left of this one also coming out. Both of them will be dot out of the paper, so cannot be 0. B3 as same, from the I2 it is coming in, from the I1 also coming in, so cannot be 0. Both of them are coming in. 0 here means that the magnetic field must be in opposite direction. So the high probability to make the magnetic field is 0 is in between. Maybe in the equations that to the left or to the right, it is okay, no problem. But here, because we have the same electric current coming up, so maybe it is in between. Because if we talk about the I1 and in B2, it will be coming in, and if we talk about I2 in B2, it will be coming out. So something like that. Let's say the distance between we want to find two wires. We can set, for example, from here to here is R, and here to here will be 1 meter minus R, because we don't know what is R. So must be something like this. B1, let's say BA, X and Y. Bx will be the same with by. Bx is mu 0 ix per 2 p rx. Here mu 0 iy per 2 p ry. 2p we can cancel, mu 0 we can cancel. Ix is 2, rx we have r. Then iy we have 4, per ry we have 1 minus r. So we have 4r equals to 1 minus r. We have 4r equal to minus 2r. R we have 4r minus plus 2r equals to 6r equal to, or we have r is 2 per 6 or 1 per 3, something like that. So for the magnetic field having 0 in total, 0 magnetic field, we have to make sure that all if we have 2, both B having the opposite direction. So we can do something like this. You have to find it. Which one? It can be in between, it can be to the left, it can be to the right. So that's some example related to long straight wire, loop, and also solenoid. Only long straight wire, loop, or solenoid, or it can be combined. Now, I want you to check your classroom. I already put the assignment there related to this one. I want you to solve it, and if you have any difficulties accessing the link, let me know so I can help you and submit it before the end of the session. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh. See you.